Hello everyone, welcome back to PyMan Tutoring. This is part 2 of our exploration of the derivative function. And in this video, we're going to be looking at how we do the derivatives of exponential functions. And this is going to introduce us to Euler's number, which is commonly known as E. E is a very important number in calculus, as we shall see. So let's begin. In the previous video, we looked at doing derivatives from first principles for simple polynomial functions. Now we're looking at the case of exponential functions. And if you remember, when we say an exponential function, we mean y, which we can now write also as a function of x, is equal to some base to the power of x. This is our basic exponential function, and we know what it looks like. The basic shape of these exponential functions is that they pass through 0, 1, increase steeply in this fashion. So here's f of x, and here's x. And if, for example, we were looking at 2 to the x as our particular function, so an a value of 2, then we would expect that the function is equal to 2 when x is equal to 1. And we would expect that once we got up to a value of 2, we would have a function value of 4 when x is 2. Okay, so the question we're being asked is, well, what is the slope of the tangent to this curve at any particular point we happen to choose? Can we do a derivative from first principles on a function like this? Obviously, we can see that the slope is getting steeper and steeper as x increases. But it's getting steeper and steeper in a particular way. If we look at this simple table of values, we can see that between x equals 1 and x equals 2, we have a change in f of x of 2 and a change in x of 1. So we have a slope of 2. Between x equals 2 and x equals 3, we have a change in value of 4 for a change in value of x of just 1. So our slope is now increased. And so I think we can see that our rate of change is related to the value of the function at that point. Let's just do one more. At 4, 2 to the power of 4 would be 16. And so between these two values, we've increased by 8. X has increased by 1, and so we have a slope of 8. So our slope is very much related to the value of the function at that point. And so you might be tempted to say, well, it looks like f dashed of x, the derivative of x, is just the value of the function at that point, a to the x. And you're not too far away, but the problem is we haven't actually done the derivative from first principles correctly. We haven't reduced the delta x down to 0. We haven't found the limit as delta x tends to 0. And we need to do that in order to get the correct expression here. So let's take a look at what happens. So our usual notation, we will say f dashed of x. And let's get used to writing also the Leibniz notation, dy by dx or even df by dx is okay too. And all of these things mean the limit as h tends to 0 of f of x plus h minus f of x divided by h. So let's plug in our function. So f of x plus h in this case means a to the power of x plus h minus f of x, which is just a to the x, and divided by h. Now what can we do? We can use our exponent rules. Remember that a to the m plus n is the same as a to the m, a to the n. So we can break this first term into the product of two exponents, and that'll be useful. That gives us the limit as h tends to 0 of a to the x, a to the h minus a to the x over h. Now if you notice, we have a common factor of a to the x on top. And since a to the x does not contain any h, it can be pulled outside of the limit without affecting the calculation. So let's make some space over here so we can keep this all on the same page. So let's continue up here. We can pull out that a to the x. So we've got a to the x limit as h tends to 0. What are we left with? Well, we've got a to the h minus 1 divided by h. So as we saw earlier, we thought maybe the derivative of a to the x was just a to the x, and sure enough there is an a to the x there, but we've got this second piece, this weird limit, and we don't know what to do with that. The best we can do at this stage is look at some values of that to give us a clue as to what that means. So let's do that on the next page. Let's find out what that strange limit thing is. So we've seen that if f of x is a to the x, then df by dx f dashed of x turns out to be the original function multiplied by the limit as h tends to 0 of a to the h minus 1 divided by h. So let's take the example of a equals 2, so that the f of x is our old friend 2 to the x. And then we would get that f dashed of x would simply be 2 to the x multiplied by the limit as h tends to 0 of 2 to the h minus 1 divided by h. Okay, so let's put in some numbers as we did when we were calculating instantaneous rates of change. Instead of letting h be 0, let's put in some small values of h and see what happens. Okay, so let's make a little table. We'll take different values of h and we'll calculate 2 to the h minus 1 over h. So when h is 0.001 are 2 to the h minus 1 divided by h. If you plug that in your calculator, you'll get something like 0.6933875, and so on. If we go a few more digits, let's make h really small. Let's put 6 zeros in there. We're getting really close to 0. Nothing much changes. We get 0.6931. We're only changing the fourth decimal place here. And you'll find if you keep putting in smaller and smaller values of h, this function does indeed appear to be approaching some kind of tangible limit, somewhere around 0.6931. Let's try a different base now. Let's suppose we had f of x was 4 to the x. What would that look like? So now we'd be looking at values of h and values of 4 to the h minus 1 over h. Let's go in with a nice small number again, 0.000001. Let's calculate this value. So if we plug that into our calculators, we get a value of 1.3863. Interesting. Let's do another base. Let's say we have f of x is 8 to the power of x. We'll feed in the same value of h. And what do we get this time? Plug it into your calculator, you'll get 2.079. And in both of these cases, if you feed in even smaller values of h, you'll find that the result is very, very close to these numbers. So what are these strange numbers that are appearing? Why is the differential of 2 to the x just 2 to the x multiplied by this number? The differential of 4 to the x is just 4 to the x multiplied by this number. And the differential of 8 to the x is just 8 to the x multiplied by this strange number. So one of the clues is by looking at the ratio of these numbers. If we look at the ratio of this pair, plug that into your calculator, you'll find that it's very close to 2. And if you take the ratio of this pair, you will find that it's very close to 3. So let's look at this a slightly different way. We've got the limit as h tends to 0 of 2 to the h minus 1 over h. This is in the case where a equals 2. And we have found that is equal to 0.69. Let's just call that for now the number L. We have found that the limit as h tends to 0 of 4 to the h minus 1 over h comes out to be 2 lots of L. And the limit as h tends to 0 of 8 to the h minus 1 over h appears to be 3 lots of L. Now let's write these second two rows in a slightly different way. Let's write that 4 as 2 squared, so we can write the limit as h tends to 0, 2 to the h squared minus 1 over h. Notice I flipped around these two exponents. I can do that because if you remember, a power to a power is just the product of those powers. So 2h and h2 are the same thing. So I can write it in this fashion just for clarity on what I'm about to show. And the limit as h tends to 0 of 2 to the h cubed minus 1 over h. All right, so what do we see here? We see that we're increasing the exponent on this function, and the result we're getting is a multiple. We're increasing the exponent on the function, and the result we're getting is that multiple of the original value. So where have you seen this before? Well, you've seen it in logarithms. Let's take a look. Suppose the log of 2, don't worry about the base for now, let's assume it's base 10. The log in base 10 of 2, let's say that is equal to some number k. The log of 2 squared is 2 times the log of 2, which is 2k. And the log of 2 cubed is 3 times the log of 2, which is 3k. So here we see the same pattern. We're increasing the exponent of the number we're operating on with this function, and the result we're getting is just a multiple of the base function. So it appears very much as though this function up here has logarithmic properties. And so let's just write that this is the log in some base, we don't know what that base is, of a. And let's in fact give it a special log notation. Ln stands for natural log of a. If you look on your calculator, you will see that next to the regular log button, log, there is a button that says ln, which stands for natural log. So where have we arrived at? We have said that if y or f of x is equal to some base to the power of x, then dy by dx, which is also called df by dx, which is also called f dashed of x, is going to be equal to the original function a to the x multiplied by the natural log of a. So what we're saying is that when we do the derivative, or we differentiate the function a to the x, we end up with a new function that has the log of the base as the scale factor. So in the case of 2 to the x, we end up with 2 to the x multiplied by log of 2, which we saw was 2 to the x times 0.69 roughly. And so we're going to end up with a graph that is compressed. in the vertical axis because we have this 0.69 scale factor. And that means that the slope of this exponential curve at any point on that curve is given by the value of this new function. So some quick examples: if f of x was 8 to the power of x, then f dashed of x is very simply the original function multiplied by the log of the base, the natural log of the base. F of x equals 1/2 to the x, and then f dashed of x is 1/2 to the x, the original function, multiplied by the natural log of 1/2. So let's just write that again. F of x is a to the x, f dashed of x is a to the x multiplied by the natural log of a. But we still don't know what is the base of this natural log thing. Natural log is the log in some base that we don't know. If we knew what that base was, then we would have a very special function, because the log in base 2, for example, of 2 is equal to 1. The log in base n of n is equal to 1. And that means that if we can find the base of this natural log, then this piece of the derivative can be reduced down to 1, and we would actually have a function which was its own derivative. So what is that number? Well, we found that if a is equal to 2, the natural log was 0.6931. If you put in a value of 3, you'll find that the natural log is 1.0986, something like that. And we're looking for the case where the log of the number, we're looking for the natural log of some magic number that is equal to 1. So we can see that it's somewhere between 2 and 3, and probably closer to 3 based on this 1.0986. And if you play on your calculator and keep plugging in numbers, you will find that the value of a you're looking for is 2.7182818828, and then it goes on and on and on and on. And this magic number is called Euler's number. And in mathematics, we give it the letter E. So basically, we're saying that the natural log of a number is the log of that number in base E. And so what's special about that again? So if we're going to use E as the base of our exponent, so that our f of x is actually e to the x, then f dashed of x will be e to the x multiplied by the natural log of e, which is e to the x multiplied by the log in base e of e, which is just e to the x. So e to the x is magical. It is its own derivative. And that makes it really important in calculus. It can greatly simplify calculations. And graphically, what does it mean? Well, it means that if I draw a graph of y equals e to the x, then the slope, the value of the slope, the tangent slope at any point is exactly equal to the value of the function at that location. So what have we learned in this lesson? We've learned that if you have a graph of y equals a to the x, which is f of x, then the slope of that graph, dy by dx, or f dashed of x, is equal to that function multiplied by the natural log of the base. And therefore, if y is equal to Euler's number to the power of x, then we have the special case that the derivative f dashed of x is equal to the original function. So you now know how to do the derivatives of exponents, and you've had a brief introduction to natural logs and Euler's number. In the next video, we'll take this a little further and show you where Euler's number comes from, and then we'll move on to the derivatives of trigonometric functions. Hope this has made sense, and don't forget to like and subscribe. And also, if you have any particular topics you'd like me to cover, drop me a comment and I'll do my best to prioritize those subjects. Thank you very much.